Okay, I'm in the last little part of this really large packet.
Go Eagles.
It's
Very large.
been skipping around. Did we finish all the stuff in 6.5? Like the expanding and condensing ones?
Yes.
Oh yeah, did we do the change of base ones?
I mean, probably did. I just don't know what you're
Yeah.
talking about. We left out.
Yes, those ones.
Yes.
Okay.
We did.
So just as a little refresher, because I did see that's like important to know how to type those into your calculator. What we talked about, I know it's been a while, on Friday was to evaluate something like this that's asking me 3 to what power gives me 8. That's not something we know off the top of our head. You take the log of the like bigger sized text number divided by the log of the base. Base always goes on bottom to figure that out. So for this one, if I did that quick, actually I had the answer right here. I got about 1.893, which makes sense because 3 squared is 9, so we should get a number that's a little under 2. So that's how you, or you can use natural logs too. You could also do the natural log of 8 divided by the natural log of 3, and you get the same number. That little formula works for that as well. Okay. That was kind of the end of that lesson, and then we did like those log properties, those 3 properties: product, quotient, and power are your 3 log properties. And those are going to come into play when we solve equations. Okay, so I feel like this is the most important of the log lessons because, like I said, as I was looking over the practice problems, I saw a couple exponential equations, which you wouldn't have known how to solve those without logarithms. These exponential equations, you can write this here if you want to. So now we're going to solve exponential and log equations. Exponential equations are obviously the ones where the variable is in the power spot, where I'm trying to figure out what the power is, and that's what logs helps us do. Logs evaluate power. A log equation looks something like this, where we have a logarithm within the equation. Okay? All right, now, some exponential equations you probably could do in your head, such as this one. This is asking you 5 to what power would give you 25. What would that be? X would have to be 2, right? Because we know 5 squared is 25. All right, 2 to what power would give me the square root of 2? Any guesses? 2 to what power gives me the square root of 2? Probably should write on that. Fraction, think fraction.
1.
Close. 1/2. If it's a square root, the denominator is always like what the index is of the radical. Index meaning like what you're rooting. If you're cube rooting, it's 1/3. If you're fifth rooting something, it's 1/5 power. Okay. Ooh. Little trickier. What we could do for this one, I'm like, I know 8 is 2 to the power of 3. I know 8 is 2 cubed. I can almost like rewrite this so that they have the same base. And then you can figure out what x is, or then you could set the powers equal to each other. If you have the same base, these powers are going to have to be the same. Or think what minus 5 would give me 3? 8. 8. I'll show you how to algebraically do this in a second, but it's good to know what we're really solving for. Now, number 4, we don't know how to do this one off the top of my head. 2 to what power gives me 10? I don't know. But what I do know is I can evaluate log base 2 of 10, and that would tell me that power. That's what a logarithm is, right? This is asking you 2 to what power gives me 10. And then I can do this in my calculator using change of base by doing log of 10 divided by log of 2. And we get about 3.3. Let me get a better number here. I just wrote 3.3. Log of 10, close the parenthesis, divided by log of 2, close the parenthesis, 3.3219, dot, dot, dot. And again, that number makes sense because 2 to the power of 3 is 8, 2 to the power of 4 is 16, so that number is in between 3 and 4, a little closer to 3. Okay, that's just to get you thinking into what exponential equations are. So I'm going to show you how to solve these now, technically like algebraically, without just like looking at it and figuring out what it is in your head. It's kind of like this equation right here. If you have 2 times some number gives you 4, a lot of you could tell me, oh, x is obviously going to be 2 because 2 times 2 is 4. But algebraically, what we could do is like take off the layers around x, divide this side, do inverse operations to isolate my variable, and we get that. And there is a way to do that with exponential equations using inverse operations, and that's what we're going to do. Okay, so this is weird. Really formatted. First example here. If you have something like this, 100 to the power of x equals 1/10 to the power of x minus 3. If you have x's kind of like on both sides, it's going to be one where you can rewrite both bases using a common base. So think of the number 100 and 110. I could rewrite both of those with a base of 10. Like 100 is 10 squared, and 1/10 is 10 to the negative first. Okay? So first thing you should kind of check in an exponential equation is like, can I rewrite both sides with the same base? So 100 is 10 squared, so I have 10 squared to the power of x. And then 1/10 is 10 to the negative first, and that's being raised to the x minus 3 power. Okay, you can just see I just rewrote those red numbers with the base of 10. And then we can kind of use some exponent properties here. If I have a power to a power, I'd multiply those. So that's the same as 10 to the 2 times x is 2x. Here, 10 to the negative 1 times x minus 3, or I got to multiply those exponents. I'm going to have to distribute. I get negative x plus 3. Power to a power, you multiply those. In that case, you have to distribute. So then from here, this is kind of like that one we did with the number 3 and the little exploration. Here, if you have the same base, you can just set the powers equal to each other. We get x to be 1 and solve it that way. Okay, so check first. Can I rewrite it with the same base? If you can just solve from there by getting the bases to be the same and then setting the powers equal to each other. Now, about 90% of the time with exponential equations, it's not going to be that way. Like number 2, where I could not rewrite the number 7 as 2 to some power, right? I can't rewrite a base of 2 using a base of 7, where that's not like an option here, I guess, is I can't physically rewrite those numbers. So here's where logs come into play. All right, now, if this equation was 2 times x, you don't have to write this down, just look up here for a second. This equation was 2 times x. You guys have been doing this for a long time. You know the inverse operation of multiplication is division. You would divide both sides by 2 to get rid of that, and we get 7/2. All right, so here's the important connection. This is not 2 times x. This is 2 to the power of x. So I need to undo the base of 2. Inverse operation of exponents or exponential functions are log functions. So how I can undo a base of 2 is I can take log base 2, because that's the base on this exponential equation, log base 2 of both sides of the equation. All right, so here's my equation. 2 to the x equals 7. So I took log base 2 of both sides. Log base 2. Reason why, we talked about this, I think, a little bit on Thursday. When you have these matching bases, they're inverse operations. Those undo each other. And that's also asking you 2 to what power gives you 2 to the x. So you're just left with x x is log base 2 of 7, which makes sense, folks, because this question, this log is asking you 2 to what power gives you 7, and that's what this equation is asking you. 2 to what power gives you 7, right? So this like process works, and then to type this in your calculator, we have to do the change of base. We have to do log of 7 divided by the log of 2, which I got about 2.807. So that's the algebraic way to solving exponential equations is you use logarithms. Okay, we're going to try a bunch more. I'm trying to find the one that was a log equation on the packet, but oh, number 72 was an exponential equation 72. Okay, let's try a harder one. I don't know why my this is so weird. Let me quick just here's okay, next page. We're gonna try more. Number 3 is an example of an exponential equation because where is my variable? Up in the power spot. I always teach solving equations as we're just like taking off the layers around x, especially when there's only one variable term. So I kind of see this equation as I have 3 layers around x. I have plus 4, I have a base 10, and I have a times by 3. So what feels like the easiest like first layer to get rid of here? Yeah, get rid of that 4. It's exactly what I would do. Get rid of the 4. Then I have 10 to the 3x equals 5. Now be careful. This is 10 to the power of 3x, not 10 times 3x. So to get rid of base 10, I take log base 10 of both sides, which is my common log. If you want to write this, you can. But also, if we don't write a base on a log, we just assume it's base 10. So I take log base 10 of both sides. And guys, we can do whatever we want in an equation as long as we do it to both sides. Just got to be consistent. So that would get rid of that base of 10. That would undo that layer. They're inverse operations. And I'd have 3x. Now here, I don't need to do change of base in my calculator because I have the common log button. I can just take log of 5. I'll do that in a second. Log of 5. You could do change of base if you didn't recognize that. You're going to get the same number. However, I'm not done solving for x. I see I have 3 times x, so I'd have to finish by dividing both sides by 3. And then I usually type this like in my calculator all in one step. I do log of 5 and then divide that whole value by 3. It's not the log of 5/3. That's different. You want to do log of 5. I'll pull my dot just for the sake of looking at trying this. Okay. So you'd want to do log of 5. Close that. You can even hit enter if you want, and then divide that whole thing by 3. That's good enough. So we get about 0.233. Okay. Try another one. This time I see 4 layers on my variable. I have this minus 7. I have this times 4. I have a base of e, and I have a times a negative 0.3. So there's a lot I got to do, but the easiest first one to do would get rid of that 7. Add 7 to both sides. And then I get here. Now, before we get rid of the base e, I got to get rid of that times 4. So I would divide both sides by 4 first to get rid of that 4. So you basically take off as many layers around x as you can until you get stuck with your variable up in the power spot. So we're stuck here. Okay, I don't want to divide both sides by negative 0.3 yet. I gotta get rid of that base e. So I would take log base what of both sides? What's my base on this? E, which is natural log. I would take the natural log of this side. So the only time you do the natural log of both sides is if it's a base e. This special base gets a special log. If you want to write in base e, you can. You don't have to. You most commonly won't see that written. Those have matching bases, so they undo each other. We get here. We don't need to do change of base because my calculator has a natural log button. So the last step I would have to do is divide that answer, the natural log of 5, by negative 0.3. So natural log of 5, close that, divide by negative 0.3. There's my answer there, about negative 5.36. Okay. Kind of makes sense. Inverse operations, just picture it as they're like taking off the layers around x, just like you normally do when you solve equations with like multiplication and division and square roots and all that stuff. You just use inverse operation to isolate the variable. So, all right, let's try a few more. So number 1's a little different because I have variables on both sides, and I see this one has a base of 5 and this one has a base of 25. So this is the one, kind of like the one we did with 100 and 1/10, where I could rewrite both sides with a base of 5. Because 25 is 5 squared. And then you don't even have to change the other side. So here, I would do power to a power. I'd multiply those. That's the same as 5 to the 2x minus 10. There's kind of 2 ways you could go about this now that I showed you how to do the other ones. At this point, you could do log base 5 of both sides and get rid of the bases, or just use like a little, I don't know, common sense is the right word. Just use like a little pattern recognition here that like, hey, if I have the same bases, the powers also have to be the same. What you can't do, folks, you can't do like log base 5 of one side and log base 25 of the other side to get rid of the bases. You can't do that. You got to do the same thing to both sides. So you'd have to do this first, or you could do this, log base 5 of both sides. Either way, you have to do the same base on both sides. There is a way to do it when you don't have the same. I don't think that is like in pre-calc, so I don't think that would show up on the clip. All right, we get x to be 7. Okay. Let's do 2 more. So here, I only have 2 layers around x. I have a base of 7. And then I have 9 times my power. What would my first step be?
To divide
By what?
by 7.
It's not 7 times 9x. It's 7 to the power. So the inverse operation of exponents log base what?
It's not. No, wait. Oh, 7.
Log base 7 of both sides. Yep. So that's my base here. And again, just gotta do it to both sides. You can kind of, you get to decide, but it has to be to both sides because that will undo that layer. That would give me 9x. Now this over here, I can't do base 7 in my calculator, so I'm gonna have to do that little change of base formula. Oh, this would be a good one to do in our calculator together. Figure out what that is, and then divide it all by 9. So I'd have to do log of 15, close that, divided by log of 7, base always goes on bottom. Figure out what that is, then divide that all by 9. And that's would be how you got that answer. 0.155.
So why do you? So when you write log base 7, you have to put 7 to the 9x or to the whatever because that's like it's all one. Because like you do log base 7 of 7 to the power of 9x. So like you put. Because I was just confused why you do 2 7s, but I guess.
Oh, so here's my equation, right?
Yeah.
So I'm just doing the red part to both sides, the log base 7.
Yeah.
So this 7 was like in my
Oh,
equation.
so because okay. I think I was confused because 7 to the 9x 1.
Yes.
Not 2 7. That's
Right.
what I was getting.
Yep. And the reason why we picked 7 is because so those would cancel out.
Mm-hmm.
Yep. Good question. We can do the one on the clef together after this. Okay, one more with E. So here, subtract 16, that'd give us negative 11. Divide by negative 2 first. Gives me 11 halves. Okay, what would I do next? Natural log on both sides. Good. And you can write it right in your work like this if you want. You can just like write it like that. I just usually do it as 2 steps to kind of like show in my videos and stuff. That would undo that. We get 2x is the natural log of 11 halves, and I put that in parentheses because it's the natural log of that whole fraction, not the natural log of 11 divided by 2. It's the natural log of 11 over 2, and then I would divide that by 2. Okay, so in your calculator, you would do the natural log of 11 halves, or 11 over 2, figure out what that is, and then divide that answer by 2. We get 0.852.
Do you just do natural logs of 11 over 2 because there's no base? Or like why do you?
Right. Well, because we have a natural log button in our calculator. So we don't need to do like the change of base formula. Your calculator can do log base 10 and it can do natural log. Anything else, 15, 41, anything else you have to do like the change of base using the common log button.
Okay.
Yeah, but that one, correct.
It's like above the e's or the. Oh, that's kind of.
Because the last one was log base 7, right?
Is it just natural? Natural log e?
Yep, those undo each other because this has a base of E.
I wrote it wrong.
And if it helps you to write in the base, you can see that. You can do that.
Okay. Yeah, that's why I always get
Yeah. Okay, so I'm going to turn to that one in the clef packet if you have that with you. If not, and you want to try it on your own, that's fine. It's number 72. Now this one is probably, I mean, you could maybe figure out this one without me teaching you logarithms. Because you can do it by rewriting the base. Oh, sorry, it's not equals 16, it equals 64. We could still rewrite the base. So you can do this 2 ways. You could do, hey, I know 64 is 4 cubed. And then just set the powers equal to each other. and we get 3 halves. Or you can use logs. So I could take log base 4 both sides. If this makes more sense to you, because you're like very like, I like step-by-step algebra solving techniques, this works. You can take log base 4 both sides. That would undo that. We get 2x. Now we technically don't need our calculator for this. This is ask me 4 to what power gives me 64. That's 3. Or use a calculator if you need to. You get 3 halves.
So for the one above at 71,
Mm-hmm.
do you just, it's saying like, what x to what power equals 2? Or no.
Yeah, we can do that one quick. So that's saying, and we're going to do log equations. Okay, we're going to rewrite this in exponential form. It's x is my base.
Mm-hmm.
X to the power of 2
Equals 5.
So what would x be? I'd have to square root of both sides. Maybe the square root of 5. So that's a. Okay, there's another good problem. Let's look at 76 quick. 76. So this one says if 20 equals 3 to the power of x, which of the following expresses x as a base 10 logarithm? That's my common base. Okay. So think of how you would solve this. You would take the log base what of both sides? 3. Good. Log base 3 both sides. Because that would get rid of that. All right, I'm just going to move it over here. So now this is not base 10, this is base 3. So this is kind of like asking you to apply the change of base formula, but I've been showing you guys how you would type that in your calculator is the log of 20 divided by the log of 3. That's base 10. I find it very strange that on this exam they write in base 10. I've literally never seen that before, that they actually write in base 10. But that's fine. That's like almost more helpful. Then you don't have to know that the common log is base 10. It's written there for you. So which of those options would be correct? It'd be E. E there is log base 10 of 20 divided by log base 10 of 3. So that's kind of like a solving one. Like, the math isn't hard. It's just like the notation is what trips people up on logarithms. I feel like that might have been all for exponential equations. 50?
Yeah.
Okay, let's look at that one.
Maybe I'm just
Ooh, that's a good one. Okay, so this, we kind of talked about it. I will go back to my notes really quick. Let's see, which ones did we graph logs? I think that was 6.3. I think. Let me see if that's right. Okay, yeah. So I don't remember which day we did this, but we like briefly talked about how like logs and exponents are inverses of each other, and how like the domain for exponential functions, the domain is all reals and the range is just positives because we don't get out any negative values. So since these are inverses of each other, all their x values and all their y values flip-flop, and that's why when you like find inverse, you switch the x and y, you're flip-flopping the domain and range. So that's what this is saying here. So now the domain for logs is just positives. That's the range. And the range is all reals. Okay. So number 50 says, which of the following would be true for some function that's log base 2 of x? And we're actually going to solve log equations, and with these, you have to remember that the domain is just positive, so this might help you kind of remember it. So number 1 says the domain is 0 to infinity. Now, the reason why that one is false is because it's including 0. And there's an asymptote here. We can't take the log of 0. You can try this in your calculator. Take the log of 0. It's going to tell you domain error. So the only piece that makes this false is because they put a closed bracket here. You guys know that notation, right? That means like including 0. So that one's false. All right, the next one says the range is negative infinity to infinity. And that's the same as all real numbers. The range is negative infinity to infinity. That means all real numbers. So that's true. All right, now the third one is that g of x is increasing. Where is it? Increases with increasing x values. All right, now this is the part, and I think I mentioned this. I could be wrong, but this is the one where I said, hey, it's nice because these properties like still hold true. Like for exponential growth, if the base is big, it's growing. If the base is small, it's decaying with exponential growth. That same holds true for logs. If this base is greater than 1, it's still logarithmic growth. It's technically increasing. It's very slow logarithmic growth. If that base is in between 0 and something like this, then it's going to decrease. So that one's also true. So it should be D, right? D is 2 and 3 only for number 50. Yeah, D. So that's like kind of a good example of like, you kind of have to know what the graphs are, but you won't be like asked to actually like graph one, but just know those relationships. Now, I had this little like cheat sheet of when I tutored in college, when I tutored college algebra, this class that you're like trying to exempt yourself from. I made them like this cheat sheet of all the different types of functions and like all the domains and ranges. I'll see if I can dig that out of my college laptop. That might be helpful for you guys. Okay, let's solve some log equations quick. So sorry, back to these ones. We can skip the explanation or the exploration. All right, so log equations, and I didn't see any on this practice test, but if they're asking you to solve exponential equations, this is fair game too. These go hand in hand. So log equations are easy to detect because they literally have the word log or natural log in them. All right, so when you have a log in the equation, you want to get rid of it using its inverse operation, which is exponents. Okay, so it's kind of similar to the ones we just did, but now you're looking at what the base of your log is. So here I see natural log. Everybody find this problem? An example number 2, I think. What's my base on this natural log? E. If you want to write it in, you can. E. So what I'm going to do is I'm going to exponentiate. I always struggle to say that. Exponentiate both sides with a base of E. So I'm going to take E, and I'm essentially raising both sides as an exponent. And we can do this as long as we do it to both sides. What that does is that gets rid of the log. They're inverses of each other. And I'd be left with 4x minus 7 equals x plus 5. And I did have you practice like some canceling properties with these ones as well, where the logs were in the power spot. Because of their relationship, they undo each other. Here I can just quickly solve for x then. We get 4. All right, now here's the part where the domain of logs comes into play, kind of like that question. We can only take the log of positive numbers. And again, test this in your calculator. Take the log of -7. It's going to tell you domain error. So anytime you're solving a log equation, you just have to make sure that when you plug it back in here, you get a positive value. So for example, 16 minus 7, I don't even need to know what that is. I know it's positive. We're good. 4 plus 5, that's obviously going to be positive. Okay, this fits in my domain. Oh, I know. Do you remember when you did like square root equations in algebra and sometimes you got extraneous solutions? Yeah, this is kind of like that too because you have a restricted domain with logs. I think it comes up later in the notes. Okay, so let's try another one. So this one's obviously a log equation. I see the word log. Log base what in number 2? 2. So I'm going to exponentiate both sides with a base of 2. Isn't that weird? With a base of 2. 2 to the power of log base 2. Those are inverse operations. They cancel each other out. I'm left with 5x minus 17. Now careful here. This isn't 2 times 3. It's 2 to the power of 3. That's 8. 2 to the power of 3. We're exponentiating both sides. All right. And then I can quickly solve. Get x cubed 5. Let's make sure when I do 5 times 5, 25 minus 17. Yep, we're positive. We're good. That's all I really make my students show for checking me. Like, can I just show, yep, positive. We're good. Okay. What do we got for time? So these ones, I look at this one, I see log base 3, so I would exponentiate both sides with base of 3. That would undo that logarithm. I have 2x plus 1 equals 3 to the power 2 is 9. That's all it is. I think these ones are almost like easier for students to visualize, and it's less kind of like work you have to do, but some of them can get tricky. So this one I have log base 6 on both sides, so I'm going to do 6 as my base, exponentiate both sides to get rid of that log. Okay. Some party. Is that from the wrestling room?
Yeah. Isn't it? Yeah.
Yeah.
Gym class.
Okay, let's do one more and then we'll save the rest tomorrow. So sometimes it might be a little more complicated, and this is where properties of logs come into play. Okay, let me show you what you can't do first. Let me show you a non-example, so don't write this down, because this is a non-example. This is what you can't do. You cannot, well, first of all, let me ask you this. What's the base on this log? 10. When there's not one written, we assume it's 10. I can't do this, unfortunately. Because then you're like exponentiating with a base of 10 like twice on one side and only once on the other side. So you can't do that. Some students try to. What you can do is you can condense this into one log. One big happy log family. Let's see if we remember this. So if I'm adding these logs, do you remember what we do with the 2x and the x minus 5? Multiply, yep. You're going to have to distribute. You're going to multiply those together. Remember doing that?
Yes.
Okay. So let's simplify that a little bit. We get 2x squared minus 10x. So you have to condense first. And it's kind of like when you solve an equation and you have more than one variable, you got to combine your like terms first, then take off the layers around x. So that's what we have to do here, kind of combine our like terms first. Now we can start getting rid of the layers around x. So this is base 10, so I'm going to do base 10 and exponentiate both sides. That would undo that common log. I would get 2x squared minus 10x equals 10 to the power 2 is 100. And it looks like I'm left with something I might have to factor to solve. Because I see an x squared and x. I'm resulted with a quadratic equation. So let's quick do that. Set it equal to 0. I would divide both sides by 2. Work with smaller numbers. Anytime I can factor with smaller numbers is good for me.
Can you have 2 answers for that?
Yes, but sometimes one ends up being extraneous. But it is possible to have 2 answers.
You have to put 2 on the outside though.
No,
Still.
2 doesn't.
Oh, this 2?
Yeah, since we took it out. I mean, since we divided by 2, we have to like. Oh. I was thinking.
Like keep it out here?
Yeah, but no, you just divide.
Since it's an equation, we can divide. Yep, good question. If it was just asked to factor, we could not do that. All right, so this factor is what? X minus 10, x plus 5, right? That would work? Yep, that's right. X minus 10, x plus 5. So we get solutions of 10 and negative 5. And Sophie asked a great question. Can we get 2 solutions? Yes, you can. But there is one of these that when I go to plug it back in to this, or this, whatever one, 2 times negative 5, I'd be taking the log of negative 10. We can't do that. 2 times 10 is 20. Log of 20, that's fine. 10 minus 5 is 5. Okay, yep, that's positive. This one's good. So this one ends up being extraneous.
Wait, so the answer is 10 and, or just
10.
Just 10.
Yep. Now, sometimes when people solve these and they get a negative answer, they're like, oh, my domain is only positives. You have to be careful because look at this. If the equation was the opposite of x and you got negative 5, that'd be fine. Negative 1 times negative. Then you're taking log of positive 5. That's still okay. So just because you get a negative solution doesn't always mean it's extraneous. You gotta go back and see what your arguments are, what you're taking the log of. Okay, folks. Good start. So if you want to practice some logs in ALEKS tonight, that would be fun.